June and I are going to give you the preview or give you the overview about the CaffeOnSpark. This is an open source package we just released several weeks back. So I will try to talk. I give the talk, and June will give you an interesting demo. Okay. So in the talk, I will first try to explain why we believe deep learning and Spark need to come together. And if you guys remember, this morning, both Jeff Dean and Andrew was talking about the deep learning. And then one of the slides that Andrew gave was the Superman of the Spark versus Superman of AI. I think it's all believed that those should be the team. Even better could be one single Superman both do the Spark and AI. So that's so we talk about that, and we walk through the architecture of the CaffeOnSpark, and then June will come up to give you the very detailed demos of using the CaffeOnSpark using the Python notebook. So as this morning, you guys already heard enough story about the deep learning, right? Deep learning is a branch of AI. It tries to simulate how, as a human being, you are learning from all this massive data through a deep, many layers of the neural network. And so typically, those neural networks tend to be very deep, like a very simple ones. It could even have a few dozen of the layers, and some others could be over 100 layers. And then when you do the learning, you're going to sort of input the layers, learn from the data. You gradually, through layer by the layer, you learn the high-level abstractions. Then you they come back, you apply the gradient back propagations, try to adjust the parameter you have for your model. You keep going through that process. At the end, you will come up very good models about the data, right? So here's as an example. So at Yahoo, we have a photo service called Flickr. And so many of you, hopefully you are familiar with, you're either using Flickr or using similar services. Now with the smartphone or the digital camera at hand, many of us take a lot of pictures, right? So now a typical way, so the online photo service organize your picture is by dates. So as you keep taking pictures, at some point you're going to say, okay, I have a lot of pictures over there, but I want to find a particular picture. How are you going to do it, right? And then it's all believed the technology like deep learning should be applied here and should be, make that beneficial for all users. So as an example, so what we decided to do from Yahoo, we introduced a new capability we call it the magic view. So this magic is a magic of AI, right? So what does that enable us to do is as a user, when you go to our Flickr service, instead of navigating your pictures through dates, you just go through the bunch of the categories. And those the tag of the classification of your picture against those category is done by deep learning. So as you could see, some picture I have in the forest, on the mountains, next to the buildings, or even a particular type of the architecture form. Then if you look at those, as a user, I never really give those the details since. Then if you look at them, it's really quite accurate, even so it's not 100%. If you see one of the pictures over there look like an arch, but it's not, it's not. But overall, I think so this is a feature from a user point of view. You do not need to do all those things. We just apply the a deep learning capability to do the job for our users. So now let's take a look at what we do, how we come up with the classifications for all your picture. At the back of our process in our Flickr services, we actually going through this simple pipeline, four-stage pipelines, to come up with the tag for your pictures. First, we prepare the data sets for the training. Then we apply the deep learning to come up with the high-level abstraction of the features. And then we apply the traditional classification algorithms to come up with the classification models. Then finally, we apply the model against the billions of the pictures. So because of the number of the data we have and every day our users upload our pictures, this whole pipeline is happening on the big data technology, such as Hadoop, Spark, and Storm. So, so one of the untold stories, though, is in the early days of our pipeline, we actually have two different clusters. One side is the deep learning cluster, the other side is the big data cluster. So then we're using those two clusters try to do the job for your picture classifications. So here's what we do, right? So using your Spark or Hadoop, prepare your data sets to clean up whatever you needed to do. And then transfer those data sets from big data cluster to the deep learning cluster. Over there, we apply deep learning capabilities, come up a model. Once you have a model, ship the model over to the big data side, then over there at the end, you try to come up with your final models for your classifications. And this is the two cluster models actually cause a lot of headache. Because many times you do not really come up with this magic model once. Your scientists need to come up with all different idea about your models and try the different data sets, all those things. So as a result, like this moving back and forth between those two clusters actually causing both the productivity issues and the quality issues of our model. So instead to solve this problem, so we thought, won't it be nice if you could do this big data processing and deep learning things in a single cluster, right? Then by being a fan of Spark, then I thought, why don't you just use Spark? Spark sometimes has all the capability in it. You have all the SQL things, you have a bunch of dozens of machine learning libraries in it. Then, once you go through all those, capability of the Spark, then you realize I do not find any capability for deep learning. Right? Now, so then the question is, how are we going to introduce a deep learning capability into this Spark? Then we certainly have a few choices. One choice is just do this thing from ground up, which we thought that's nuts. Then instead, what we wanted to do is build on top of the work deep learning community has done over years. So as you saw in the several other talk, including this morning or including the battle talk, you saw that the several framework that's already available for us to use from the deep learning communities. So there's the Caffe, there's the TensorFlow, there's the Cyano, there's the Torch, and a bunch of those. And in our use case, we decided to actually focus on Caffe because the Caffe is quite a mature, among the other technology, it's a relatively more mature technology, and it's very popular in the vision community if you're thinking about our Flick use case. And then we are able to extend the Caffe beyond the vision. So as a result, we decided to work on the CaffeOnSpark. We have been working on it for several quarters now. And then in the early this year, we decided to open source our CaffeOnSpark technology as an open source, under the Apache license. Then what it is designed to do is try to fill the gap we noticed in the Spark ecosystem. We wanted to have a capability to do the distributed deep learning. And instead of to make this capability only available for Yahoo clusters, we decided to make it easily useful for anybody in the communities. So as June going to give you the demo about how to use the CaffeOnSpark on EC2, right? So from an architecture point of view, it's a relatively simple idea, right? So you have for the people who, in the Spark application, you have the Spark drivers, you have Spark executors. So what we decided to do is embed the deep learning library like a Caffe inside the executor. So at that stage, as a simple, right? So then we realized, if for the deep learnings, you really need to go through your data many iterations. And your model tended to be quite big, right? Very easily millions of the parameters. And then the number of iterations you need to go through is millions of them. So instead of depending on the driver to exchange the information for the learning from each executors, we decided to have our executor talk with each other. So in this sequentially, what we do is that for each executor, going to pick a mini batch from their local partition of data, do a learning a little bit. Then at that point, we using the communication between our executors to share what they learned. At that point, so everybody have the same picture about what the model should be at this stage. Then go to learn next mini batch, then keep exchange. So at the end, by the many iterations, at the end, you will get a nice model that learned from the whole data sets. So to verify the usefulness of the distributed learning, we did a quick benchmark in the early stage of our project. So on the X dimension here is the number of hours we are spending on the learning. And then the Y dimension here is as the time progress, how the error or the accuracy is being improved. So if you saw here, like the top line is that is the single GPU line. That's like after 3 days, we are achieved about like 60% accuracy, right? If you're thinking about, is the model going to not be useful until you have 10%, 90% accuracy at least? Then it's going to take a long, if you look at the slope, it's going to take a long time to get in there. So on the other hand, if you look into the other line over there, for example, for the 4 nodes ones, within 10 hours, we achieve like 80% accuracy, right? So, I think this is a demonstration about how you leverage the distributed capability of the Caffe and the deep learning capability like Caffe and Spark, put them together should enable us to get an accurate model more quickly, be able to use all those things. So for the Spark users, you may be happy to know that using CaffeOnSpark is really easy. Use your favorite command, Spark submit. Just like in any Spark applications, you could launch this thing on your single node or in a cluster. And for the CaffeOnSpark, we even enable to specify what is the network connectivity between your executors. So you could specify Ethernet or InfiniBand or whatever the new network connectivity we may introduce in the future. So more specifically, for example, you could even specify the number of the executors you're going to use, the number of the GPU or CPU you're going to use for each devices, and you specify configurations. And for the configuration, you may also happy to know the configuration file of the CaffeOnSpark logically is the same configuration file you're going to use for your Caffe. So over there, you simply need to specify the HDF locations of your data sets, and it's the format you want. For example, we even support your traditional LMDB format, in addition to like the other fancy format like data frame. And for the advanced users, we introduced some API for you to use. So for example, we have Scala APIs. Very easily you could say, here's my configuration, here's my CaffeOnSpark object. From this particular data source, I'm going to do the training. For this particular data source, I'm going to extract the features. And the feature we extracted is actually represented in the data frame format. So as a result, you could easily apply the feature you extract from deep learning to use it for your classification or whatever your traditional machine learning algorithm as you like. And similarly, we have a Python API that enable you to do the job very easily. And once you use those things, then when you launch your job, you will be able to leverage the UI from Spark, the UI from the Cafe, those things, right? For example, here you will see, go to your Spark UI, you will see the progress you are making in your job. And on the other side, you will see the details about how the accuracy is being improved as you are going through at this point. Okay, so talk is easy. So let me have June to give you the demo.
Hi everybody, my name is June. Next I'll give a live demo on this CaffeOnSpark. Let me see. So basically, I try to use this IPython notebook to run the training and the test and the feature extraction. So the idea is this: we basically ran the two GPU instances at the EC2. Then we launched a server there, and now this IPython notebook basically connects to that server. And I will show you how we can run the training on this. Just for the sake of time, we're going to do this. This really it's a hello world application for the deep learning. So you see, this is basically it's a blank. It's a template. So I'm trying to fill in all these blank cells. So let me just copy paste. I already have the script, so I just copy paste, and you will see that it should just run. So the first step is to import a bunch of modules, and nothing special about that. So next thing I want to show that what is the training data. Actually, in this case, I'm showing the test data, but it's more or less the same. So I want to load the data, and you can see now. Maybe make it a little bit larger. Yeah. So basically, what I did is I read the data. And I show the first five samples. So as you can see, we have an index, and we have a label, and this is the image. So the goal is to recognize those images and give the correct labels. So before we go to training, actually, the other thing I want to show you is the network. So what kind of network are we going to use for this deep learning training? So there's an API actually you can use to show the network. So let me try this one. Oh, here we go. So this is the network we're going to try. So you see that there's a this is the input. The memory data layer is the input, and you get the data. You go through the convolutional layer, pooling layer, and another convolution, another pooling, and there's an inner product layer. And you get the rectifier layer, and there's another IP2, another inner product layer, and then you get you reach this last layer. So with that, let me try to train, and I'll explain the command here. So because the training takes time, so let me launch it right away. So now the training has been launched. So let me just explain what these are. So the first line, basically, you instantiate a CaffeOn class object. Then once you have this object, then you provide the arguments. You specify what kind of configuration. If you're familiar with Cafe, this is basically Cafe proto text definition, and also you need to specify where you want to save the model. So for this particular example, the model is saved. The model is saved at the HDFS. Also, the data itself also is read from the HDFS. And you specify the devices, number of devices per node. So in this case, we only have one GPU per node. So and also with the cluster size, we have two nodes. So the cluster size is 2, and the connections. In this case, we use Ethernet as the communication, the physical layer basically. But at Yahoo, we have options to use the RDMA, which is much faster than this version. So you get a source, and the API is pretty simple. You take the object and you call the train, and you provide the source. and you're wrong. So while it's running, let's check, check the GUI here. So see if the job actually is running. So this is the application ID, detail UI. So if you're familiar with Spark, this basically is the Spark job tracker. So it will tell you what the stages this is on. So right now it's yeah, the number is moving, so it's good. It's running. So actually you'll run multiple stages. I think about 30 stages for this particular case. And while it's running, let me explain what's really going on here. So so we have 2 instances, right? We have 2 instances. Everybody grab a mini batch. So each of them grab a mini batch, and they feed the data, and they go through this network, and you do a round trip. So there's a forward path. Basically, it's calculated the output of each layer, and then you reach this last layer, and you go back, calculate the gradient. So everybody calculates their own gradient. Then once one iteration is finished, the gradient is ready, they exchange. That's why we have this Ethernet option. So basically, the workers actually they talk to each other. They exchange information over the Ethernet, and they average the gradient, and then update again, and then do another. They fetch another mini batch, then they do another iteration, and so on and so forth. And that's how it works. Let's see. Oh, it's finished already. Okay, that was fast. So we have finished the training. So next thing I'm going to do is do a test. So test is it was very fast. So you grab another data set and you say, hey, I have the model. Can you recognize the image and tell me is it 1 or 0 or whatever it is? And you compare with the ground truth, and you look at the accuracy. In this case, the accuracy is 98.97%. So it's pretty high. So that was a test. So next thing I want to do is feature extraction. So a lot of times you actually don't, the accuracy is not the only thing you care. You actually want to extract features for the next stage in the pipeline. And so a lot of times you take an image and you want to extract what's really inside of this this image. So that we call it feature extraction. So for that purpose, let me do this. So what this is, I'll extract the three columns basically. One is the accuracy. The other one's IP1, IP2. Just to remind you, what is IP1, IP2? So IP1 is here, this output. So this output is IP1, and this output is IP2. Basically, the inner product output, and accuracy, of course, is from this layer. Now I basically show them in this table, and you have all these rows. Each row actually is a sample, and you have accuracy. You have this IP1, IP2. These are vectors, and you have a label. So now we have the features. The next thing I will do is I want to show you how to do a prediction with this thing. So since you already have this IP2, I think it is based on IP2. Yeah, it's based on IP2. So you have IP2. You look at the IP2 and say, okay, these are scores basically. What's the score you get for 0 and 1 and 2 and so on and so forth. And you get you take the maximum score, and that's basically the prediction. The index of the score is the prediction. Now you get this one is 7. But for this thing, because it's almost like a 100% accurate, so you get a pretty good prediction here. So that was prediction. And the nice thing about this is you had a data frame in a Spark data frame. Now you can convert it to pandas. So basically, this is the Python pandas data frame. So you can convert them back and forth. So next thing I want to show, the last thing I want to show is the pipeline. So you can take the feature and you can feed it to a different library, different algorithm. Let's say you extract the features and you wanna on top of the deep learning, you wanna put some non-deep learning, traditional technique, right? Machine learning technique. For example, in this example, I used logistic regression. So you take the IP1 here. So this is the row.ip1. So you take that as your feature, and this is like a new data set. You put it into the pipe that thing to the logistic regression, and on top of that you can do a prediction. Of course, for this particular example, I mean, it probably doesn't make much difference because it's already so good. But in real life, situation, sometimes it pays to actually have a different stage. You basically stack multiple machine learning algorithms to get a better performance. So in this case, I mean, it's already correct. So not much gain we get from this step. So with that, I think I'll conclude my demo. And so Andy will continue with the slide. It's not coming back.
It's coming. Oh.
It's coming
okay,
back.
so assure me now your comments, CaffeOnSpark work, right? So I think we believe it's a good starting point to bring the deep learning onto the Spark. And in the coming week, we're going to introduce more capability into the CaffeOnSpark. So for example, we heard from our user communities, they really want to do the validation during the training. So in the next 2 weeks or so, we're going to introduce those features. And soon after that, we will have the LSTM support in the CaffeOnSpark as well. Then some other additional capability will be introduced later on. Then before I wrap up, I want to mention that there are several other solutions to bring the deep learning onto the Spark. For example, there is a project called SparkNet, and then deep learning for J. And so they compare with the CaffeOnSpark, they take a very simple approach. So you have the driver, you have the executor, inside the executor you do the job. And then you simply using a driver to do the communication between your models for your deep learning. So from our use case point of view, we strongly believe if you apply this kind of very simple architecture, your driver will become the bottleneck, and you will. So that's why we decided to try a slightly different architecture in the CaffeOnSpark. So I want to just summarize. As now the CaffeOnSpark is ready for everybody to use. It has been tested in our production for quite a while now. And for example, also Flickr's demo I gave you earlier on that was based on the CaffeOnSpark. With the CaffeOnSpark, we have been able to reduce the training latencies and actually improve the qualities of our auto tag and other capabilities in our applications. And also, as you saw, it's just your favorite command, Spark submit. So there's no excuse you guys could not do the deep learning. Okay? So please check out the code from our GitHub and also send us any feedback in the mailing list. Thank you.
Any questions for the folks at Yahoo? We have time for probably one question.
So in your demo, you said 2 nodes, right? So are those 2 worker nodes or 2 total nodes? I mean, is there any best practice with regards to co-locating the master along with the worker node, or you always keep the master node separate?
We have 2 worker nodes, actually. Master is separate. Yeah. Altogether, you have 3 nodes, but 2 GPU nodes. The master doesn't have a GPU, just a regular, CPU node.
Okay, thank you.